In the previous video, we introduced the Laplace transform as a black box, essentially, that takes in a function of little f of t. So little f of t goes in, and we call the machine capital script L like that, and the output would be capital F of S. And all we really know about that transform right now is given to us by this table that I've put in here. It tells us for various little f of t functions what the output capital F of S is. But we saw in the last video that the Laplace transform is linear, and that allows us to then find Laplace transforms of somewhat more complicated functions that are combinations of the ones we have here in this table. Now, associated with the Laplace transform is going to be another transform that takes us back. So this is like the idea of when we have a function. For some functions, we also have an inverse, the inverse function. And if we were using functions, we indicate the inverse of a function, little f, by little f with a superscript of -1. So we do the same thing here. If we use a script L with a -1, quote, exponent, then that's the inverse Laplace transform. So what that does is it takes a capital F of S and gives back a little f of t. And we can understand, or we can actually find inverse Laplace transforms by using the table that we have here. So for instance, if I wanted the inverse Laplace transform of 2 over s cubed, then what I do is I go to the right side of the table, find 2 over s cubed, and then look at what's on the left side, and that's t squared. So the inverse Laplace transform of 2 over s cubed is t squared. That one was fairly trivial to see, but let's take a look at one that might be a little more complicated, although not much. If we take, say, for instance, the inverse Laplace transform of s over s squared plus, say, 4, then looking at the table, we can see that that looks like our last entry on the right-hand side if a had a value of 2. So this would give us then that the inverse Laplace transform would be a cosine, and it would be the cosine of 2t. Now, one thing you might notice is that we could actually get s squared plus 4 if a was -2 as well. So that might be a little bit bothersome to us, but if we think about it for a minute, let me just put here cosine of -2t with a question mark, because that's what we would get if a was -2 rather than +2. But remember, cosine is an even function, which means that cosine of -2t is actually equal to cosine of 2t. So these two things are equal. So it really wouldn't be ambiguous to have that 4 there. Let's do another couple. In particular, let's just take a look at 2 involving the exponential function. So if I have the inverse Laplace transform of, say, 1 over s minus 5, then you can see that that has the form that we see across from e to the at. A would be 5, so the inverse Laplace transform would be e to the 5t. The one that's a tiny bit trickier, but not really all that hard, is if we have something like the inverse Laplace transform of 1 over s plus 3, say, and we can see there isn't a 1 over s plus something in our table, but we can alter the form of what we have. This would be 1 over s minus -3. And so now it looks like the form 1 over s minus a, where a has the value of -3. So this would be an e to the at, e to the minus 3t. Okay, so that's the general idea of how the Laplace transform, or the inverse Laplace transform works using the table. But of course, the functions we've been working with here are not terribly complicated. So let's look at what we do in a situation where things are just a little bit more complicated. So on this next page, I've reproduced the same table. And let's start off with the idea, the fact that the inverse Laplace transform is a linear transform, just like the Laplace transform. So that means basically that it, quote, distributes across plus signs and passes through constants. So I could then do something like this. I could look at the inverse Laplace transform of, let's say, how about 7 over s squared plus, let's say, let's do something a little easier this first time. Let's do 3 over s minus 5. Okay, so if I'm looking for the Laplace transform here, I can split the Laplace transform up amongst the two parts. So I have the inverse Laplace, I'm sorry, it's the inverse Laplace transform of 7 over s squared plus the inverse Laplace transform of 3 over s minus 5. And then we look at the numerators. If we look at our table, we know the inverse transform of 1 over s squared, but not 7 over s squared. But that 7 is really a constant. It's really 7 times 1 over s squared. And so we can bring the 7 out, just like we bring it out of an integral. And in fact, we'll find later that the transform is, in a sense, it really is an integral. So we're doing the same thing we did back in an integral calculus class when we pulled constants out of integrals. So I can pull the 7 out. I've got the inverse Laplace transform of 1 over s squared. On the other part, I can do the same thing. I can pull the 3 out, and I've got the inverse Laplace transform of 1 over s minus 5. And now we can go to the table and see that the inverse Laplace transform of 1 over s squared is just t. And the inverse Laplace transform of 1 over s minus 5 is e to the 5t. So that's the inverse Laplace transform of 7 over s squared plus 3 over s minus 5. Let's look at one more example here. Let's suppose that we wanted the inverse Laplace transform of, let's say, 7 over s squared plus 9. Now, in this case, we would recognize we don't have an s in the numerator, so this isn't the cosine. So the closest thing we can see in the table is this guy. But the problem is that the numerator we would want to be 3 because our a squared is 9, so a must be 3. So we'd like a numerator of 3, and we can get that by simply understanding or noticing that 7 is really 7/3 times 3. So I can replace the 7 in the numerator with 7/3 times 3. In the denominator, I have s squared plus 9, or let me write the 9 as 3 squared. And then because of the linearity, we can bring the 7/3 out. So we have 7/3, the inverse Laplace transform of 3 over s squared plus 3 squared. So now that's the correct form to show us that the our inverse Laplace transform will be a sine function. So this then turns into 7/3 times the sine of at, and a is 3 in this case, so sine of 3t. So there's our inverse Laplace transform there. Again, we use the linearity. We didn't have multiple terms, but we did have a term that we then created a constant we wanted to bring out of the inverse Laplace transform operator. Okay, so that's the end of this video on the inverse Laplace transform. And what we'll do is in the next video we'll look at another technique we need for finding some other inverse Laplace transforms.